So now, taking section XX between point A and B at a distance x from origin A, we can write the bending moment equation as mxx is equal to ei d square y by dx square is equal to, now bending moment about section XX considering the left hand side of section will be, first clockwise moment due to this upward support reaction VA at a distance of x, then minus anti-clockwise moment due to this UDL of 2 kN per meter acting for a distance of x meter. So we have 2 into x, and this UDL can be assumed to act at the center at a distance of x by 2 from section XX. So we have x by 2. Now since this equation is valid between point A and B, let's put it into first partition AB, and this much part of the equation is valid between point A and B only. Next, let's move this section XX towards right beyond point B such that your section now is between point B and C at a distance x from the origin A. Now writing the bending moment equation about section XX, we see that these two terms will be valid. We see that only there is addition of this clockwise moment due to this upward UDL of 2 kN per meter acting at a distance of x minus 6 meter. So we have plus 2 into x minus 6 meter. Now this upward UDL can be assumed to act at the center at a distance of x minus 6 meter by 2. So we have x minus 6 by 2. Now since this equation is valid between point B and C, let's put it into another partition, and this much equation is valid between point B and C. Now let's move this section again towards right beyond point C such that your section XX is between point C and D at a distance x from your origin A. Now writing the bending moment about section XX considering the left hand side of section, we see that these all terms will be valid, only there is the addition of this anti-clockwise moment caused due to this downward force of 5 kN acting at a distance of x minus 9 meters. So we have minus 5 into x minus 9 meters. Now this whole equation is valid between point C and D. So let's put it into another partition, third partition C dash D, which is a final partition, and this whole equation is valid between point C and D only. So this is a bending moment equation by using the Macaulay's method. Now integrating the above equation with respect to x, we have ei into dy by dx is equal to VA into x square by 2 minus 2 into x cube by 2 into 3 plus C1, where C1 is a constant of integration. In Macaulay's method we put constant of integration in the first partition, plus 2 into x minus 6 to the power cube the whole upon 2 into 3 in second partition, minus 5 into x minus 9 square by 2 third partition, which is a final partition. Now we see that in this equation we have dy by dx term, so this is called a slope equation, since dy by dx is nothing but slope of the elastic curve of the beam. Now integrating the above equation again with respect to x, we have this dy by dx term will become y, so we have ei into y is equal to VA into x cube by 2 into 3 minus 2 into x to the power 4 by 2 into 3 into 4 plus integration of constant C1 is C1x plus C2, where C2 is another constant of integration of this equation. Again we put this in our first partition AB, plus 2 into x minus 6 to the power 4 is whole upon 2 into 3 into 4 second partition, minus 5 into x minus 9 the whole cube upon 2 into 3 third and final partition CD. Now we see that in this equation we have y term, so this equation is called as deflection equation. Our next step is to find out this constants of integration C1 and C2 by using the boundary condition.